Ladies and gentlemen, let's continue with chapter 4, the chapter in Cengel and Ghajar. It is on unsteady heat transfer or transient heat transfer, which is the study of how temperatures change as a function of time. The chapter consists out of a few parts, I think 4 parts. We've done the first part, which is the lumped system. And the important thing with a lumped system is that it works well if the resistance inside the body is small in comparison with the resistance on the outside. So if we are talking of the resistance on the inside, we are talking of the conduction resistance. The resistance on the outside would be the convection resistance. And as a rule of thumb, a good judgment rule that you can use is to say that that approach would give you reasonable answers if the resistance on the inside is 10 times smaller than on the outside. So that was the lumped system approach, and it is a very nice and easy and simple equation that we can use to get the temperature. But it gives the temperature of the body, which means it's everywhere, from the center to the surface. You cannot distinguish in the inside between different points. So that is why we go to chapter 4.2. We now want to be able to do that. And the 3 simple cases, simple cases in terms of geometry that is considered is the large plane wall, the cylinder, and the sphere. With all 3 of them, the heat transfer is one-dimensional. Okay. If the plane wall is long enough or the cylinder is long enough, then we can say the heat transfer is one-dimensional. So we've started with the energy equation, all 3 dimensions. We've looked at it, all the different terms, and we've ended up with a simpler equation, a second order partial differential equation, but very difficult to solve. And the reason is that if you want to solve something, it depends on 8 other things. You've got 8 variables that would influence the result. So to solve that, people non-dimensionalized it. They work for years to get it right. They non-dimensionalized it. And the result of that is that when you have one of the variables, then you can solve it as a function of the other 3. And you can use different analytical methods to get a solution. And one of them is the separation of a variable method that has been used in this chapter. And the result is an answer, but it gives you a Fourier type of series. Okay. So the temperature distribution, non-dimensionalized, is a function, or not a function, is a sum of an infinite number of terms. Fortunately, we have seen that the second and the third term decays very, very quickly. And it has been found through experimentation that if tau, the non-dimensionalized time, is larger than 0.2, then the result will be within 2%, which is quite reasonable if tau is larger than 0.2. And for that case, you only need to use one term, the first term. Okay. So with that, we could also manipulate the equations a little bit so that we can specifically look at the cases where we are interested in the temperature at the center. And in many cases, or in most cases, that is, as engineers, that is what we are interested in getting it at the center. So again, we can make the equation simpler, and typically, I don't know why, but the moment it's connected to this thing, then it switches itself off. Right. So there's the equation, typically for a plane wall, and as we can see, n equal 1 to infinite, a large number of terms. So if tau is larger than 0.2, we only need to use the first term, which is lambda 1. Okay? Then the second thing is at the center. At the center, that cost term would also disappear. So the equation becomes even more simpler. And together with that, we can also use that to generate what is called Heisler charts. And there are three Heisler charts, figures 4.16, 17, and 18. And on each one of them, you can get a variety of information. The first chart would help you to get the center temperature. The second one is to get the temperature anywhere else that you're interested in. And the third one is the heat transfer. Right, and that is all the theory. So let's start doing a few problems so that we can have a better feeling of how to use all the things that we've looked at and derived. Okay. Now, with the previous lecture, this was sort of a trap for me, and I actually didn't want to go into it, but at the end one of you actually saw something wrong. And it was about the last thing that we wanted to do was the Fourier number, and the Fourier number is the ratio of conduction to stored heat, the rate at which it happens. All right. Conduction would be the heat transfer coefficient multiplied by the area. And the area we are going to write as L squared, because it is in terms of a cubic meter per volume. Okay. So that is the area, and then multiplied by the temperature difference, which is delta T divided by delta L. Okay. That is the heat transfer rate, okay, which would be in watts. Okay. And the one where I've made a mistake yesterday is to look at the energy which is stored. So energy which is stored would be M Cp delta T, but not M, because then it would be joules, so it would be the mass flow rate, or M multiplied by delta T. Okay, and that is where the delta T, the missing delta T, was of yesterday. So again, to get this into watts, okay, and the mass can then be written as the density multiplied by the volume, and the volume would be L squared, and that is where, after you've cancelled everything out, you can manipulate it until it is equal to alpha multiplied by T divided by L squared. Right. So, let's start with a problem. And the problem is the following. A dead body is discovered. Okay, somebody passed away in a murder or whatever. Okay. So, and the dead body, or the length of that person is 1.7 meters. 1.7 meters in length. Okay. Now, the temperature of the body, measured now in the center of the body, and you can think yourself how that temperature is being measured. Okay. So the temperature at the center, that is why we use the 0 there. The temperature at the center of the body is measured at 25 degrees Celsius when found. And that was then at 1700 hours. So at 5 o'clock in the afternoon, the dead body is discovered, and the temperature is measured in the center of the dead body, 25 degrees Celsius. Right. So the problem is now, what was the time of death? Okay. Okay. When was a person murdered? And that is a problem. Okay. Now let's see what we can do to calculate this, or to do an estimate of that time of death. Okay. Well, let's first make an assumption and say this dead body can be assumed as approximately a cylinder. Okay, of a length of 1.7 meters and a diameter of about 300 millimeters. 300 millimeters. Okay. What would be the initial temperature of the body? The initial temperature, if the person wasn't really very sick, should be about 37 degrees Celsius. Okay. Normal human being, that is your temperature typically, 37 degrees Celsius. So that is Ti. Okay? And we can measure the temperature on the outside, the environment, or we can make an estimate of the average temperature on the outside for maybe a few hours or a day or whatever. And let's say 20 degrees Celsius temperature on the outside. Okay. And we need a heat transfer coefficient. Okay. If you go and look in your textbook, ambient air, typically a value of usually in the order of about 10, but in this case let's use 8 watts per square meter degree Celsius. Okay. We would need the properties of this body. We would need the K value and the Cp value and the density. Any suggestions? Well, if as good students you've paged through your textbook, you'll see there at the back are quite a number of tables. And during this module, you're going to use them a lot. So it's very important that you know what the information is in those tables. By the time you're going to write test or exam, most probably you're going to put in stickers and stuff like that because you need to get to that information very quickly. Right. Now, if you go through the tables, as far as I know, I haven't seen any characteristics of human flesh or meat. Okay. So, what assumption can we make? We can assume water. Let's take the characteristics of water because what 70 or 80% of your body is water. Okay. So, it's just an assumption. So, let's take the characteristics of water. Now that I tell you water, you can go and look in your tables. And if you do that, you will see there's a table which is table A9. And in table A9, lots of characteristics are given specifically for water. The steam tables is another table that you can use. Okay. Now, if you look at this table, you'll see that the pressure is given, okay, density is given for a liquid and a vapor, then the enthalpy values, specific heat values, liquid and a vapor, thermal conductivity, that is what we want, viscosity values, Prandtl numbers, and the volume expansion coefficient. But they are all given as function of temperature, from 0.01 to a temperature of 374.14. So, at what temperature would you suggest we use? Okay, what temperature do you suggest we use? If we, for example, look at 20 degrees Celsius, you will see that the thermal conductivity of water would be equal to 0.598. If you would use it at 50 degrees, it would be 0.644. Okay. So it's different, but if you look carefully, you will see it is not that much different. So it is dependent on temperature, but it's not a strong function of temperature. And the same with density, you'll see the change would be very, very small. So again, we would typically make the assumption and say, well, let's use the average between 37 and 25. The body started at 37, it's going to enter 25. Let's use the average of 25. So, we want the properties at the temperature of 37 plus 25 divided by 2. That would be the properties at 31 degrees Celsius. Right, so if you look at your tables, values are given at 30 and 35. And I don't know if you are like I am, but I don't like to do interpolation. So I will typically use the closest one, maybe 30 degrees Celsius. And if you do that, or I'm going to show you later another way that you can do it, which is better, is you can then get the values at the temperature of 31 degrees Celsius of K, which is equal to 0.617 watts per meter Kelvin, and the density, I've used 1,000 kilograms per cubic meter, and the CP value of 4178 joules per kilogram degrees Celsius. Okay, so there are the properties for water or the body. And if you want to, you can also go and calculate the thermal diffusivity, which would be K divided by rho Cp. Okay, if you do that, then it would be equal to 1.477 multiplied by 10 to the minus 7 square meters per second. Right, so those are the properties. It's available in your textbook, but it is also available on CD. So if you look at the front of your textbook, there's a disk with software which is called EES, EES. I would recommend, we are not going to have formal classes in how to use it, okay, but I would recommend that you start using it. It is a very, very powerful tool. You can put in the equations as we normally do, and you can put in the values, and it will directly calculate whatever you want. Okay. So in any complicated information, and I'm going to show you typical examples later, you can just put in the equation, you can put in all the values, and it would calculate the value that you want. But that is not really the powerful tool of it. The powerful tool of it is that in that you can get access to the database of all the information that you need. So you can, for example, put K and in brackets water, temperature that, and it would give you the values that you need, which is really very nice to use. Okay. So, okay. Now, we've got the properties that we want, and now we have to decide what method are we going to use to determine the time of death. So far, we've done two. So let's do both and see what happens, and how the results compare. Okay. So, let's try the lumped system approach. Let's try the lumped system approach. And with the lumped system approach, we have to calculate the characteristic length, which is equal to the volume divided by the square, by the surface area. Okay, now the volume of that body would be equal to pi divided by 4 multiplied by d squared multiplied by L. And that would obviously be the diameter d, and that would be the length of 1.7 meters. The surface area would be equal to pi, the diameter multiplied by L, so it is this surface on the outside, and then we still have two of these end walls. So it's 2 times pi divided by 4 multiplied by d squared. Right, I'm not going to do the substitution of all the values. The diameter is 0.3, the length is 1.7, so it's elementary. But we are going to use it, so I'm just going to write down the value of the volume, which is equal to 1.744, and the surface area, which is equal to 0.1202, and that would then give us a characteristic length of 0.0689 meters. Okay? Right. Now we want to calculate the Biot number. Yep.
So just the units of the volume will be 10 to the minus 3 meters cubed, or?
Sorry, the units of the volume is cubic.
1.744.
Which one? The 1 point?
The 1.744, the volume.
Oh, this one. Yes, what about it?
Is that in 10 to the minus 3?
No. So let me just write it there. Okay. That volume okay, is 1.744, and it's cubic meters, the units. And this is the surface area, so it's in square meters. So it would give us the characteristic length as in meters, which is then equal to 0.1202. It is equal to 0.0689 meters. That's right?
Yeah, so
What
the
does it-
values just don't make sense because the top one is larger than the bottom one.
Oh, okay. Just check where I've made a mistake. Most probably I did. Okay. You can just go back and correct the mistake. Okay, but just allow me to work through it because I want to show you the principle. Okay, ladies and gentlemen. Okay. Okay. So now we can calculate the Biot number, and the Biot number is equal to the heat transfer coefficient multiplied by the length divided by the thermal conductivity. Okay, and the heat transfer coefficient is equal to 8. The characteristic length is equal to 0.689 divided by the thermal conductivity, which is equal to 0.617. And the Biot number would be equal to 0.89. Okay? Okay. Did any one of you maybe check? Oh, is it two? Must the two just be the other way around? Okay. Sorry. Okay. So, right. So that one is 0.1202 cubic meters, and this one is 1.744 cubic meters. Is that right? Okay. Okay. If there's still a mistake, just go and correct it. Let's look at the principle further. Okay, so the calculation of the Biot number is now 0.9, which means it's almost, well, close to 1. Order of magnitude is 1. What does it mean? It means that if this is now the dead body, okay, and we look at the resistances, okay, so that resistance, if I can show the value in terms of sort of the length, would be of approximately equal length to that one. The ratio of this one to that one would be about 0.9. Okay. So it tells us that the lump system approach most probably is not going to give us a good answer. But let's just go and check what it says. Okay. Okay. So let's just make it clear. The lump system approach, okay, LSA, the lump system approach, would not be accurate. Wouldn't be accurate. So let's go and calculate the non-dimensionalized temperature. The temperature is function of time minus T infinite, Ti minus T infinite is equal to E minus B T, okay, where B is equal to the heat transfer coefficient multiplied by the surface area divided by rho, the volume, and Cp. Right, again it's elementary. The heat transfer coefficient is 8, okay. The surface area, that value, 1.744, the density 1,000, the volume 0.1202, and Cp is 4178. So you can just go and do the substitution at home and just check my calculations. But B would then be equal to 0.123402778, small value. Okay. So the non-dimensionalized temperature, which is then the temperature at time t minus T infinite, Ti minus T infinite would then be equal to E to the minus 0.1234278T. Okay, so the temperature at time t, what would that temperature be? We've got a body at 37 degrees Celsius, and now the temperature decreases, and when it was found, it was 25. So that is the temperature at time t, it's 25. Okay. The temperature of the environment is 20. The initial temperature before death must have been approximately 37, and again, that temperature should be 20. Okay. And that again is then E to the minus that, and from that we can very easily solve the temperature as 44,047 seconds, which is 12.24 hours. So that is how long the body would have taken to decrease in temperature from 37 degrees Celsius to 25 degrees Celsius. Okay. So the time of death, must have been approximately at 4 o'clock in the morning, 46 minutes. Okay. However, we know that the Biot number tells us that the ratio of the resistances are not good. Okay. So most probably it's not going to give us an accurate result. So let's go to the theory in paragraph 4.2 that we've done just now. Okay, that we've already done. So again, in table 4.2, on table 4.1, if we look at this table, we can see this is the temperature of the plane wall, and that one is for the cylinder. Okay, do you agree? So that is the equation for the cylinder. Okay. Now, ladies and gentlemen, okay. We are lazy, or I'm lazy, so the first thing I'm going to do is I'm going to assume tau is larger than 0.2. I cannot work out tau now because I don't have the time. Okay. So I'm going to assume that, which means I'm just going to use one term. And then secondly, the temperature was measured at the center, which means that that part also disappears. So the equation becomes a little bit simpler. Okay. And the equation at the end of the day is all about the Biot number. So if we look in table 4.2, for a cylinder, in table 4.2, okay. For a cylinder with a Biot number of 0.89, okay, or about 0.9, the values are given. Okay. So for a cylinder, a Biot of 0.89, I'm going to use 0.9. Then lambda 1 would be equal to 1.2048, and A1 would be equal to 1.1902. And I'm going to assume tau is larger than 0.2. I cannot work out tau now because I need the time, and I don't have the time. Okay. So I'm going to assume that, and then we've done it yesterday. It is in your textbook, or you can derive it very easily from that equation. The temperature at the center, the non-dimensionalized temperature at the center, which would be T0 to indicate it's at the center, minus the environment temperature, the initial temperature minus the environment temperature, is equal to, very simply, A1E to the minus lambda 1 squared tau. So again, T0 is the temperature at the center, which is 25 degrees Celsius. That is where it was measured. The environment temperature 20. The initial temperature of the body 37. Again, the environment temperature 20 is equal to A1, 1.1902, e to the minus lambda 1, and lambda is equal to 1.2048 square, multiplied by the non-dimensionalized time. And from this, I can solve the non-dimensionalized time as 0.963. Fortunately, it is larger than 0.2, so I can say the one-term approximation is valid. I can use the one-term approximation. Okay. And tau, which is equal to 0.963, is also equal to alpha t divided by R0 squared. Okay. And that is equal to 0.963 is equal to alpha, which is 1.477 multiplied by 10 to the minus 7 multiplied by time t divided by the radius square. The radius would be 150 millimeters, from which I can solve the time, which is a large number of seconds, 146,722 seconds, which is 41 hours. So, more than 3 days. Are you happy? Make sense? No. It's all wrong. It's a big trap. What is wrong? Everything. Okay, what's everything?
You can't assume it's a cylinder, you can't assume that the average temperature is 3 degrees.
No, I don't think so. It's a good engineering approach. But the principle should always be correct. And there's something wrong with the principle. Yes?
So you use the lump system instead of the normal cylinders
Yes. You've got it. Okay. So previously I told you that with a lump system, the lump system approach and the others. Okay. With the lump system approach, you have to calculate the characteristic length, as we've done, by using the volume divided by the area. And then the Biot number would be equal to the heat transfer coefficient multiplied by the characteristic length divided by the thermal conductivity. Okay? But for the others, when you calculate the characteristic length, it doesn't have it. And the Biot number is not based on the characteristic length. You have to go and check in the derivation what was used with the calculation of the Biot number. And that's the fine print that you have to be careful for. So, and that fine print is actually everywhere. You must just know about it. Okay. So if we look at the first table, where these equations are given. Remember here at the bottom I told you how everything should be calculated. And what do you see at the bottom? How the Biot number should be calculated. It should be calculated based on the radius, which is totally different than the characteristic length. Okay? I can just get my pages. Okay. So, ladies and gentlemen, what you should do is now looking at this problem and say, this is all rubbish. Okay, big mistake. Big mistake, that's not correct. So, what we should have done is to calculate the Biot number as specified. Where did it come from? It came from all the calculations and derivations where that was a group of dimension of or values with dimensions, and where it could have been non-dimensionalized, and that is where it comes from. So, for a cylinder, the Biot number should be calculated as the heat transfer coefficient multiplied by the radius divided by the thermal conductivity. And not on the characteristic length. So, if we now repeat this problem and do the calculation, then the heat transfer coefficient is 8. The radius is 0.15. The thermal conductivity of water is 0.167. And now the Biot number is 1.944. Much different than previously. So it's going to have a huge influence on your calculations. Right. So for that Biot number of 1.944, can go and get lambda 1, which is equal to 1.5995, A1, which is equal to 1.3384, and now calculate the temperature at the center, which is equal to the center temperature minus the environment temperature, the initial temperature minus the environment temperature. Okay, is equal to A1 e to the minus lambda 1 square multiplied by tau, the non-dimensionalized time. Okay. The temperature at the center was measured, 25. The environment temperature, 20. The initial temperature, 37. Again, the environment temperature 20 is equal to A1, 1.3384 e to the minus 1.5995 square multiplied by tau. Calculate the non-dimensionalized temperature. Fortunately, it is equal to 0.6466. Okay. It is larger than 0.2. Why is that important? Because if it is larger than 0.2, then the error in our calculation would be less than 2%, which is fine. Okay, so that's okay. And from that, we can say it is equal to alpha t divided by R0 square. And then calculate the non-dimensionalized time, or not the non-dimensionalized time, but the time in seconds as 98,517, which gives us about 27.4 hours. Okay. The lump system approach, 12 hours. The more accurate one, 27 hours. And the trap. Don't fall into it. I told you there's a very important paragraph that confuses many students. I've made it very clear to you. This calculation of the characteristic length you only use for the lump system, and then you calculate that Biot number. For all the others, you do it differently, so don't do it the same. Any questions, ladies and gentlemen? Nothing. Thank you very much.